Good evening. We are going into our next session of that chapter, Work Energy Power. And today we'll be discussing the topics potential energy, kinetic energy, and conservation of mechanical energy. Now, here, potential energy you've learned in class 9 as a work done when you need to carry a book or any body through a height. So, let's consider a body of mass m, and let's say this body of mass m is taken from here and displaced through a height h. Okay, so the work done, as we know, is equal to f d cos theta, where f is the force acting on it, d is the displacement, and theta is the angle between the force and the displacement. So you are now taking this book up, and the force that you are applied is in this direction. Okay, but the force acting on this in the downward direction, that is the gravitational force, will be acting in the downward direction. So here the force, the external work that you must do to carry this object to a height h will be its weight. Force is the weight m into g. The displacement is through a height h, and cos 0, because force and displacement is in the applied force and the displacement are in the same direction. So I've taken cos 0. Cos 0 is 1. So this work done by this external agency to take this body from here to a height h is what you have called as potential energy, denoted by V. Now this work is done against the gravitational force F. So this potential energy is the work done or the energy stored when work is done against the gravitational force. That energy stored in the body is what you call as potential energy. Its SI unit is joules. Just like energy, its SI unit is joules, and it's a scalar quantity because you see it's a dot product between the acceleration. Acceleration, you know, is a vector quantity. Displacement is a vector quantity. You take the dot product between the two quantities and you get a scalar quantity. So potential is a potential energy, and potential both are scalar quantities. Also, its dimensional formula, you know, is ml square t raised to minus 2. Force is ml t raised to minus 2 multiplied by the displacement. You have ml square t raised to minus 2 as the dimensional formula for potential energy. So now, one thing you would have noticed is that in our formula, we are only interested in the initial position and the final position, because potential energy we know is mgh. So this h depends on the difference, the displacement through which you've taken, the height through which the body has been taken. So now, suppose, so if the potential energy here is 0, then the potential energy here is mg into h. So the 0 of the potential energy is arbitrary, which means, suppose, let's say we have 3 points like this. We have a point A here, we have a point B here, if you have a point C here. Now suppose you assign this potential energy at this point as 0 and this is h, then the potential energy here will be mgh. And if this is also h, then the potential energy here has to be, potential energy at A has to be 2 times mgh, because the total distance from here it has been taken up is 2h. So this is how, so this is arbitrary. Now suppose you had assigned this position to be potential energy as 0, then this would have been simply mgh between these 2 points, the distance being h. So that's why I told you the 0 of the potential energy is arbitrary. With respect to this is at a potential mgh. But if with respect to this point is at a potential 2 mgh. So for convenience, we have set the ground level always as 0 of the potential energy. So that is why we always measure the height through which a body has been taken from the ground level, because for our convenience, we have taken the ground as a 0 of the potential energy. Okay. Now also, you see, we define V as mgh. Now you will notice that the force acting on, in this case, force F can be defined as the negative of the derivative of potential. Let me show you how. This is minus d by dh of V is mgh. That means minus mass and g being a constant, we may take it out d by dh of h. I've already taught you that d by dx of x raised to n is equal to n into x raised to n minus 1, right? So d by dh of h here, power 1, should be equal to 1 into h raised to 1 minus 1, which is 1 into h raised to 0, that is 1. So this is going to be minus mg, which is a force acting on this body. Force is as you take this body upwards, you are doing work against the gravitational force I told you, and the gravitational force is minus mg because it is acting in the downward direction. So we see that in this case, this force can be defined as the negative of the derivative of a scalar quantity, like in our case it is the potential. Such a force is what you call as a conservative force. So conservative forces can be defined as the negative of the derivative of a scalar quantity. In our case it is the potential. Such a force is called a conservative force. Now there are two other properties I want to discuss about this conservative force. Now let us take two arbitrary points like this. Two arbitrary points, positions of the body. Let's say initial position I'm going to call as xi, and the final position where I take the body upwards is xf. Now here I may write f is minus dv by dx if we are talking about a conservative force like the gravitational force acting on this. So then I said if it's a conservative force, you may express the conservative force as a negative of the derivative of a scalar quantity. Here we have potential. Or I may write f into dx is equal to minus dv. Now if I am going to find this, so this is for a small interval dx, we have a change in potential as dv. Now if I am going to integrate over or add up this whole thing over the interval from initial position to final position, then this would be integral from xi to xf, f dx should be equal to the minus of integral. Let's say the potential here is vi and the potential here is vf. This is going to be integral dv from vi to vf. Or I may write this as this force f into integral dx xi to xf. Or wait, this is equal to, what is integral of dv? Integral of x dx is equal to x raised to n plus 1 by n plus 1. Now if it is simply integral dx, then we have 1 here, 1 into dx. So it is equivalent to writing x raised to 0 dx, right? Because x raised to 0 is 1. So integral simply dx can be written as integral x raised to 0 dx, which is x raised to 0 plus 1 by 0 plus 1, which is x. So please remember, integral dx is x. So in this case, we have integral dv should be simply v within the limits vi to vf. So we may write integral xi to xf f dx is equal to minus of this v will first take the upper limit, which is vf, minus this v will then take the lower limit vi. Or this f dx, you know, is a small work done. F into dx would be the small work done to move this from this point to this point, if this displacement is dx. Now from xi to xf, when I add the small work done, I get the total work done in moving the body from xi to xf, which is going to be equal to vi minus vf. Now this is an important result which we need to define this conservative force. You will see that if a conservative force is acting on a body, the work done by it depends only on the initial position and the final position, the potential energy at the initial position and the final position, independent of the path taken. That means if you're taking a book from, let's say, a body from this point to this point, you may take it from here and bring it here in the shortest path possible, or you may say, let us say we first take it to some point here and then bring it here. But however, when you calculate the total work done, we are only interested in Vi minus Vf, not on the path taken. It is independent. The work done by such a force is independent of the path taken. Depends only on the initial position and the final position alone. Vi minus Vf. So another property of this work done, the conservative force is that it is path independent. It does not depend on the path taken. Depends only on the initial and final position. Also remember, if you are taking the body through a closed path, that is, you took it up from Vi, Xi, you brought it up to Xf, and you brought it back to Xi. Now what will happen is, Vi minus, the final potential is also Vi. So Vi minus Vi, the work done is going to become equal to 0. So work done by a conservative force in a closed path will be 0. So we discussed three properties of this conservative force here now. One, we can express the conservative force as the negative of the derivative of a scalar quantity, like potential in this case. Also, the work done depends only on the initial position and the final position, not on the path taken. Also, if the body is taken through a closed path, then the work done will be 0. One example that we now dealt with for a conservative force is a gravitational force. In the next session, I will be dealing with another conservative force, that is a spring force. Then next year, 12th standard, we will be dealing with electrostatic force, which is also a conservative force. So every time you read about a conservative force, you should know that the properties of these conservative forces are what we discuss now. There are non-conservative forces like dissipative forces like the air resistance or the frictional forces, which actually take energy away from the system, and such forces are called non-conservative force because they do depend on the path taken. For example, suppose let's say I'm going from my house to the end of the road. If I have the choice of two paths, one, a very smooth tarred road, frictionless, and I have another road which is a very rough patch, the work done as I move from my house to the end of the road, it does depend on the path taken, right? If I take the frictionless path, then there is no work done against frictional forces. But if I'm taking the rough path, then work is done against the frictional forces, which is lost in the form of heat is produced, energy is lost in the form of heat and sound. And that means energy is dissipated away from the system, taken away from the system. You're not going to get it back. So work done does depend on the path taken. Also, if I travel from my home to the end of the road and come back, the dissipative forces have taken away the energy from the system, which I'm not going to get back. So work done in that closed path will not be equal to 0. Some examples are the frictional force and the air resistance. Okay. So this is all we have to discuss about potential energy. We now next go into our topic on kinetic energy. Kinetic energy is also nothing new to you. You have dealt with that topic in class 9. You know that kinetic energy is the energy possessed by a body by virtue of its motion. So if a body of mass m is moving with a velocity v, we know that its kinetic energy is K equal to half mv square, which is actually half m into velocity being vector. It is the dot product between the two velocity vectors. Therefore, kinetic energy is a scalar quantity. And because its energy, its SI unit is joule, and its dimensional formula will be the same thing, ml square t raised to minus 2. Kinetic energy is half mv square. Okay. Then, now that we know, we've discussed both kinetic energy and potential energy. we may go into the law of conservation of mechanical energy, right? The law of conservation of mechanical energy is, see, your potential energy. We just defined, let's say F is equal to minus dV by dx, or I may write it as minus delta V by delta x, from where I will get delta V as minus F delta x. So the change in potential energy of a body, delta V, can be expressed as minus F into delta x, right? So suppose your body is, let's say, falling from some height. Okay, it's falling down. Now as it falls down, here at this position, its initial velocity is 0. So its kinetic energy is going to be equal to 0. But as it falls, its velocity is going on increasing. So the kinetic energy will start increasing as it falls. But its potential energy will start decreasing, because as it comes down, h is going on decreasing. So as the height decreases, we know that potential energy being mgh, the potential energy will decrease. So we are now going to write down delta k should be equal to force into delta x, right? Kinetic energy, as you know, is work done. Work done is force into displacement. The body is falling down. The gravitational force is acting in the downward direction. So we may write F dx, or for a displacement delta x, I may write kinetic energy is work done F into delta x. If I add the two, that is delta V plus delta k, it should be equal to 0, or delta V plus k is equal to 0, which means the change in this total energy is what you call as mechanical energy, sum of kinetic energy plus the potential energy. So the total mechanical energy, no change, there is no delta V plus k equal to 0 would mean there is no change in the total mechanical energy, which means that the total mechanical energy remains a constant. Now this is how we state law of conservation of mechanical energy. It says that if the total mechanical energy will always remain a constant if the forces acting on the system are conservative forces. Otherwise, it does not remain a constant. So if the forces acting on a system is conservative, then the total change in mechanical energy will be 0, or the total mechanical energy will always remain a constant. Potential energy will be converted to kinetic, or kinetic energy can be converted to potential, but the total mechanical energy will remain a constant. In 9th standard, we have done a very good example for this, which we need to do in 11th also. So that's what we're going to do now, to show that when a body falls from a height h, its total mechanical energy remains a constant. We're going to prove that. So for that, let's take a position here. Let me call it as A. Then we have a position B, and here we have a position C. This total height is capital H. This height I'm going to take as small h, so that this will be total h minus the small h, right? Okay. Now when the body is here at position A, you know that as in free fall, the initial velocity is 0. So naturally its kinetic energy is going to be 0. But because from the ground, we are taking this as a ground level. So from the ground, because this is at a height h, it has potential energy, and the potential energy is going to be mg, total height from here till here is h. So that the total energy is kinetic plus potential, which is mgh. Now we see at a point B. Let's see what happens at a point B. As this body falls here, it gets a velocity v, right? And I'm going to calculate the v at the velocity of the body when it has traveled through a distance h. We know the formula v square minus u square equal to 2as. So this is v square minus initial velocity is 0 equal to 2. Acceleration is the acceleration due to gravity, and the displacement of the body is h minus h. So this is h minus h. So if I calculate the kinetic energy at that point, it is half mv square, which is half into m into 2g h minus h, which is going to be mgh minus mg small h. Now the potential energy at that height, so the body is now here, from the ground it is at a height small h. So the potential energy will be mgh. So now if you take the total energy of the body, kinetic plus potential, mgh minus mgh plus mgh. So you are left with mg capital H. Okay. Now we are going to now consider this position C when it reaches here. When it reaches the ground, you know that at the ground the potential energy is 0. So potential energy is 0. The velocity when it touches this ground, v square equal to, u is 0 there, 2g. The total displacement from here till here, the displacement, because you took u as 0 here, and that's why we got v square equal to 2g. So from here till here, the displacement is capital H, 2gh. So that its kinetic energy is half m, v square is 2g into h, which is mgh. Now you will see that the total energy is equal to 0 plus this mgh is mgh. So you see at all points, and in A, at B and at C, the total energy is mg capital H, though here kinetic energy was 0, we had maximum potential energy. But as it reached C, all of the potential energy has been converted to kinetic energy, because potential energy is 0 and kinetic energy is maximum mgh. So this is how you prove total mechanical energy of the system remaining a constant if the forces acting on it is conservative. We know that as the body falls, the only force that is acting on it is the gravitational force, which is a conservative force. Now, we have dealt with both kinetic energy, potential energy, conservation of mechanical energy, and before we stop our session, we also need to discuss a very small topic on power, because it is not just enough for you to know the work done, it's also in many cases important to know the rate at which the work is done. For example, suppose you're buying a motor to pump up water from the ground to your tank on the terrace. It's not enough to know how much work the pump can do, but how fast it can pump up the water. So, power, we define power as the time rate of doing work or work done by time, which is dW by dt. Work done, I already taught you, is a dot product between F and dx, both of them being vectors. We did it in the beginning of this chapter. Work done is the dot product of F dx by dt. Now this dx by dt we know is velocity. So this is F dot v. So you see, since it is a dot product between force and velocity, we know power is a scalar quantity. This is a scalar quantity. Its SI unit is watt, and its dimensional formula will be ml square t raised to minus 3, because work done we know is ml square t raised to minus 2, divide by time and you have ml square t raised to minus 3. This is the SI unit of power. The higher units are, if you're talking about your automobile, normally your car's I think it's 1200 to 1500 horsepower. Or if you're buying your motor pump to pump up water, it will be in horsepower. So 1 horsepower is 746 watts. That's a higher unit. This is the SI unit. We also have 1 kilowatt being equal to 1000 watts. So these are the units of power that I think you have learned in 10th standard. Also, I have one more thing to discuss with you before I stop the session. That is the energy, the unit of energy, higher unit of energy called the kilowatt hour. If you check your electricity bill, you will see that the electrical energy consumed by you is given to you in kilowatt hours. So 1 kilowatt hour is, 1 kilowatt is, let's say 1000 watts multiplied, because watts is the SI unit. Hour is time, but SI unit is second. So when you convert hour to second, that will be 3600 seconds, which is 3.6 into 10 raised to 6 joules. So 1 kilowatt hour is actually the unit of energy, electrical energy usually, energy, which is 3.6 into 10 raised to 6 joules. So we'll stop our session for today. We discussed potential energy, kinetic energy, conservation of mechanical energy and power. Thank you.